Welcome to MathGPT's physics lesson on electromagnetic waves. Today we'll explore electromagnetic waves in vacuum and in matter, understanding their mathematical descriptions and physical behaviors. Electromagnetic waves are oscillations of electric and magnetic fields that propagate through space, carrying energy and momentum. These waves include visible light, radio waves, microwaves, X-rays, and many other types of radiation that make up the electromagnetic spectrum. Let's first understand sinusoidal electromagnetic waves in vacuum. Imagine a coordinate system where the wave travels along the x-axis. For a wave traveling in the positive x direction, the electric field oscillates along the y-axis, while the magnetic field oscillates along the z-axis. Notice that the electric field, magnetic field, and the direction of propagation are all perpendicular to each other. Now, let's look at the mathematical description of these waves. The electric field at position x and time t is given by E vector equals j hat times E max times cosine of kx minus omega t. Similarly, the magnetic field is described by B vector equals k hat times B max times cosine of kx minus omega t. Here, j hat represents the unit vector in the y direction, and k hat is the unit vector in the z direction. E max and B max are the maximum amplitudes of the electric and magnetic fields. K is the wave number equal to 2 pi divided by the wavelength lambda. Omega is the angular frequency equal to 2 pi times the frequency f. The term kx minus omega t indicates wave propagation in the positive x direction. If the wave was moving in the negative x direction, we would use kx plus omega t instead. An important relationship exists between the electric and magnetic fields in an electromagnetic wave. The maximum values of the fields are related by E max equals c times B max, where c is the speed of light in vacuum. This tells us that in a vacuum, the ratio of the electric field amplitude to the magnetic field amplitude is always equal to the speed of light, which is approximately 3 times 10 to the 8th meters per second. Note that c has units of meters per second, which makes this equation dimensionally consistent, as E has units of volts per meter and B has units of Teslas. Now, let's study how electromagnetic waves behave in matter. When an electromagnetic wave travels through a dielectric material, its speed is reduced compared to its speed in vacuum. The speed of an electromagnetic wave in a medium is given by V equals 1 over the square root of epsilon times mu, where epsilon is the permittivity of the material and mu is its permeability. We can express this in terms of relative constants. V equals 1 over the square root of k times km times 1 over the square root of epsilon naught times mu naught. This can be simplified to V equals c over the square root of k times km. Here, k is the dielectric constant or relative permittivity, and km is the relative permeability of the material. For most non-magnetic materials, km is approximately equal to 1. Let's visualize how an electromagnetic wave changes as it travels from vacuum into a material. As the wave enters the medium, its wavelength shortens while its frequency remains constant. This causes the wave to slow down, as the velocity equals frequency times wavelength. For example, when light travels from air into water, which has a dielectric constant of about 1.33, the speed decreases by a factor of the square root of 1.33, which is about 1.15. This change in speed causes important phenomena like refraction, where the direction of the wave changes as it crosses the boundary between media. Let's summarize what we've learned about electromagnetic waves. In vacuum, electromagnetic waves propagate at the speed of light c, with the electric and magnetic fields perpendicular to each other and to the direction of propagation. The electric and magnetic fields oscillate sinusoidally and are related by E max equals c times B max. In matter, the wave speed decreases to V equals c over the square root of k times km, where k is the dielectric constant and km is the relative permeability of the material. This change in speed leads to important phenomena like refraction when waves cross boundaries between different media. Understanding electromagnetic waves is crucial for many applications from telecommunications to optics and beyond. Thank you for watching. I hope you now have a better understanding of electromagnetic waves and their behavior in vacuum and matter.